Alright, so here's a problem. What is the major product for the reaction shown to the right here? Right, this guy. And so we have answer options down here. My suggestion, run the reaction yourself, work it out, and then match it up with the answers. So that's what we'll try to do. Right, this guy right here, copy, paste. What's going to happen? We have this guy, and we also have, we want to look at what's in the pot, right? We have acid, right? So we got some acid in there, and we got water like this, right? So let's figure out what are nucleophiles, what are electrophiles. That's the key here. So this guy right here is a electrophile, right? Because it would love some electrons. Philic love some electrons because it's just a positively charged proton, right? So our nucleophile, which loves nucleus that contains protons, so has a lot of electron density, would be this guy right here. And so then this water right here, the lone pair of electrons on the O that has a partial negative charge. So this guy right here, water, is also a nucleophile. So we want to attack electrophiles with nucleophiles. The electrons go and attack the electrophilic nucleus right there. And what that does, that's going to open this molecule up. Alright, and so then what do we have next? Alright, we got this molecule, so we replaced the double bond here. Right, so we get rid of this guy here. And what's going to happen? So this H, you can either add H here, right? Or you can add an H over here. Could go either way, right? And so if you added H here to this guy, then you'd end up with positive charge over here. And if you add H here with this guy, you end up positive charge over here, right? And so if you end up with this carbocation, that would be a 1, 2, 3 tertiary carbocation. And if you end up with this carbocation, that would be a 1, 2 secondary carbocation, right? And carbocation stability goes like this. Tertiary is more stable than secondary, which is more stable than primary for carbocations, right? So we know that the red guy here is what's going to happen, right? So we open this up, get rid of that. So we open this up, so now, right, we'd be at the next step here. Let's see, we got rid of the double bond, right? And we add an H over here, right? And we have a carbocation here. And what else do we have? Well, we have this nucleophile right up here. And so now we've got a positive charge around here, and this nucleophile, which it can go ahead and the electrons from there can attack this positively charged center, and we can go forward. Next step, right? If we just, if we just go, let's copy this, copy, paste. So now where are we? Let's see. We got rid of the double bond in the first step, right? We attacked the double bond with the proton, matching up nucleophiles to electrophiles, right? Then we added the proton to this carbon here in order to create a tertiary carbocation intermediate, which was more stable than the other possibility, right? Well, actually, at this point, after it adds, right, it doesn't have a positive charge. So let me get rid of that there. This thing is a mistake, right? So we got an H there, and then we added now H2O here. So let's see, H2O added as the nucleophile here, right? So we got H2O here, right? And then since H2O added, right, we have oxygen bonded to three things right now, so that would be a positive charge on this oxygen. But what's going to happen, right, is some base will come in and just pick off one of these protons, right? And so you'll end up with, let's see, this without this guy. So it's going to be, right, match it up to the answers. That is this guy, right? CH2, CH3, OH, CH2, CH3, OH. So our answer for this should be B. Hope that helped.